Before we get into Debye theory of solids, let's talk about normal modes. Let's consider again a crystal that has n atoms, 3n degrees of freedom, that is to say 3n oscillators. This time, the atoms are not going to be able to vibrate independently of one another. To do this, we have to employ classical mechanics to describe the system in terms of 3n normal modes. That is to say, 3n normal modes of vibration in the whole crystal. Each mode will have its own frequency, omega 1, omega 2, omega, all the way out to omega 3n. And so these lattice vibrations of the crystal are equivalent to 3n independent harmonic oscillators with those frequencies. How does this work? Well, let's start with something really simple. Let's simplify the 2 degrees of freedom first. So I have 3 masses and 2 springs, so to speak. And let's say we have a system of 2 coupled, one-dimensional oscillators. And they can be described by the following equations of motion. We use Q for position, Q1 double dot plus omega squared Q1 plus lambda Q2 is equal to 0. Q2 double dot plus omega squared Q2 plus lambda Q1 is equal to 0. Lambda is the coupling constant between those oscillators. If lambda were 0, you would have 2 independent oscillators. But lambda is not 0. We have a coupled oscillations case here. If I want to find the normal modes of vibration, what I have to do is attempt to find 2 new coordinates. We'll call them capital Q1 and capital Q2, such that when I look for their modes of vibration, they will be 2 independent oscillators. What I do is I define Q1 as little q1 plus little q2. I define q2 as little q1 minus q2. And I can substitute this into my differential equations. And what I'll get is q1 double dot plus the quantity omega squared plus lambda q1 equals 0. I'll get q2 double dot plus omega squared minus lambda q2 equals 0. Q1, capital Q1 and capital Q2 are called normal coordinates. In terms of them, the system behaves like 2 independent oscillators with frequencies omega squared plus lambda and omega squared minus lambda. We call these guys the characteristic frequencies for the system. This has enabled us to decouple the oscillators. That will give us some ammunition to move on and examine the Debye theory. So, using the normal modes of the crystal, we treat it as 3n independent oscillators now, or independent bosons, and so I can write the energy as some A equals 1 to infinity, no, I should say 3n or some number oscillators, h bar omega sub A 2 plus h bar omega divided by omega sub A divided by e to the beta h bar omega minus 1. This calculation is quite difficult to perform, but in 1912, Peter Debye devised a model that would reduce the complexity of this energy calculation and still yield predictions that matched experimental results. He introduced a continuum theory that would treat lattice vibrations and heat capacity in solids, a more realistic idea than the Einstein model provided. The idea being that if an atom in one part of a solid were to be perturbed, the other atoms around it would also be perturbed. This assumption is attributed to the fact that atoms exhibit a strong electromagnetic coupling with one another. And this disturbance would propagate through the solid as an elastic wave, analogous to the case of electromagnetic radiation and photons. So what we can do is envision this disturbance in the solid as being caused by phonons, which carry energy through the lattice. Let's characterize each normal mode of vibration by a wavelength lambda, not to be confused with the coupling constant we got rid of before. If this wavelength is much, much greater than the interatomic spacing, we'll call that x, the disturbance that propagates through the solid will displace the neighboring atoms by approximately the same amount. So this implies that normal modes of vibration of an elastic continuum approach that of a solid as long as the long wavelength criterion remains. So let's determine the specific heat and internal energy of a solid by determining the energy as a function of frequency of the normal modes. We'll go back to a very similar calculation to what we did with density of states earlier. Let's examine a cube of side L. That means volume V cubed, volume V equal to L cubed. Let's consider the elastic waves inside the cube and solve the wave equation, which we'll write as del squared of phi of r plus kappa squared phi of r equals 0. Kappa is the wave number, 2 pi over lambda. The general solution to this equation can be arrived at by applying separation of variables, so I can write my solution phi of r as a product of x, y of y, and z of z in 3 dimensions, such that phi of r is equal to a sine nx times pi x over L, sine ny pi y over L, sine ny over L, n pi nz over L. Boundary conditions dictate that phi must vanish at the walls, very similar to the black body development. And so the allowed values of k, or kappa, the wave number, would be nx times x over L, and y times y over L, and z times z over L, where n, x, n, y, and z are integers beginning with 1, 2, 3, and so on. If L is sufficiently large, the cube itself will be quite large, and then the k values will be spaced very close together, so this means we have a number of allowed values of nx, ny, and nz. Let's determine how many normal modes or energy states are allowed. So again, this is like a density of states calculation. To do this, you can envision 2 concentric spheres in kappa space, one of radius kappa, one of kappa plus d kappa. And we want to count how many states lie in the region between those 2 spheres, or 2 shells. The volume of the shell is equal to 4 pi kappa squared d kappa. Furthermore, since we're only using positive values of n, and I know you've heard this expression, we're going to use only the positive octant of the shell, where nx, ny, and nz are positive. That gives us 4 pi kappa squared d kappa divided by 8, because we're only doing that first octant. Well, to simplify matters, let's look at one dimension first. So values of kx and ky are given. The number of states that lie between kz and kz plus dkz would be dnz is equal to L over 2 pi d kappa z. This is going to work in all three dimensions. So what we can say is that the number of states where kappa lies between kappa and kappa plus d kappa, I can write as f of kappa d kappa, and that's going to be equal to v over 2 pi cubed d kappa x, d kappa y, d kappa z. Oftentimes when we talk about normal modes, we like to do it in terms of frequency rather than wave number. Omega we can write as a velocity, in this case velocity of sound times kappa. D omega can be written as velocity of sound times d kappa. So I can write my distribution f of omega d omega as volume kappa squared d kappa over 2 pi squared d kappa d omega, and that simplifies very nicely to v omega squared over 2 pi squared v sound cubed d omega. So in elastic media, for each kappa, there exist 3 independent modes of vibration, 1 longitudinal mode, and 2 transverse modes. Notice this is different than light. Light only has 2 transverse modes and no longitudinal modes. With sound or waves in elastic media, you have 3 modes. You've got 2 transverse and 1 longitudinal. So having said that, I'm going to write the above distribution in this way. I'm going to write its volume, omega squared, v omega, over 2 pi squared, times 3 over the mean velocity of sound cubed. To account for the fact that I have 2 transverse and 1 longitudinal mode, so 3 over velocity would be equal to 1 over 3 over velocity cubed would be 1 over velocity longitudinal cubed plus 2 over velocity transverse cubed. That's the abbreviation we're using. Debye assumed that the solid has a total of 3 n modes and introduced the frequency omega sub d such that if I integrate from 0 to omega sub d, and I integrate the distribution f of omega d omega, I will get the total number of modes, 3n, in the system. What that does, notice I've removed an infinity and put in an omega sub d. This tells me that there has to be a maximum allowable frequency, or by the same token, a minimum allowable wavelength, such that wavelengths that are any smaller violate the condition that lambda is much, much larger than the interatomic spacing. So instead of using infinity, I'm going to put a limit at the top of the integral of omega sub d, indicating Debye frequency. And we can determine the Debye frequency in the following way. I can just perform this integral, v times 0 to omega sub d, 3 omega squared d omega, divided by 2 pi squared v s bar cubed equals 3n. If I do the integral, I'm going to get omega sub d cubed is equal to 6 pi squared n v bar cubed divided by divided by v. I want to show you how we get there. Since v times 3 omega squared over 2 pi squared d omega over v bar cubed is equal to f of omega d omega, and v bar cubed can be written as omega d cubed v over 6 pi squared n. This gives me then f of omega d omega is equal to 9n omega squared d omega over omega sub d cubed by frequency q. So this, I can write this for my distribution. I can determine the energy then as the sum alpha a equals 1, 2, 3n h bar omega over 2 plus h bar omega sub a over e to the beta h bar omega minus 1, which I can write now as 9/8 h bar omega sub d times n plus 9n h bar omega sub d cubed integral 0 to omega sub d omega squared d omega divided by e to the beta h bar omega minus 1. Simplify it a little bit, n k theta sub d plus 9 nkt divided by x sub d cubed integral 0 to x sub d x cubed dx over e to the x minus 1, where we've defined x as beta h bar omega, which is equal to the Debye temperature divided by T. We call theta sub d the Debye temperature. That's my expression for energy. I can write my heat capacity as just the derivative of the energy with temperature. So it becomes CV is dE dt at constant V. That's going to be 3nk times 3 over x sub d cubed, integral 0 to x sub d, x to the 4th e to the x dx, divided by e to the x minus 1 quantity squared. Now, the above integral has got to be performed numerically. You're not going to do it analytically. However, we can look at the low and high temperature limits of this and get some very good information about the heat capacity. So in high temperature limit, in that case, theta sub d is much, much less than t, or x is much, much less than 1. The integrand, x to the 4th e to the x over e to the x minus 1 squared, can be written as x to the 4th e to the x divided by e to the x minus 1 times e to the x minus 1, or x to the 4th over 2 times the hyperbolic cosine of x minus 1. If we expand the cotan term in the denominator and retain only the first term of the expansion, the heat capacity will look like 3nk times 3 over x sub d cubed integral 0 to x sub d x squared dx, which is just, when I work it all out, 3nk. So in the high temperature limit, I get back the law of de Long and Petit, which I would expect to get at high temperatures, or at least room temperatures, not low temperatures. On the other hand, in the low temperature region, that is to say, theta sub d is much, much greater than the temperature, or x sub d is much, much greater than 1. The integrand approaches 0 for large values of x. So I'm going to replace the upper limit in my integral by infinity. So I get 3nk, and I get 3 over x sub d cubed times integral 0 to infinity x to the 4th e to the x dx divided by e to the x minus 1 quantity squared. That value can be tabulated. It has a value of 4 pi to the 4th over 15, giving me a specific a heat capacity of 12/5 n to the 4th, I'm sorry, pi to the 4th nk t over theta sub d cubed. So I get the required T cubed dependence as the heat capacity, for heat capacity as the temperature approaches 0. So the Debye theory works very, very well at low temperatures and at high temperatures. So this is a much needed improvement over the Einstein model for lattice vibrations in solids. Well, that concludes our course in statistical mechanics. I hope that these videos have been helpful to you. I've had a very great time doing them. You'll notice that they may be a little bit rough because we're doing them on one take only, but at least we'll have the information out there, especially in conditions when we're not allowed to come to campus or not able to come to campus. I would be remiss if I didn't thank profusely my wife and videographer, Melissa Bloss, for all of her help in this endeavor. And I wish you all well, and I wish you all safety. Thank you.